Greetings and welcome to a new video about three-phase rectifiers. In this example we'll discuss the controlled three-phase rectifiers using the thyristors, and we will discuss a resistive load in this case. We will see two operating modes or two conditions. The first one is the DCM, which is the discontinuous current mode. The next one is the continuous current mode, which is the CCM. We will see also what the differences are between each of these conduction modes. Of course, we will work out everything step by step in our calculations and verify these in MATLAB Simulink simulations. So we start first with the discontinuous current mode. The objective or our design for this example will be about a star-connected three-phase input circuit. We see here the voltages given as 400 phase voltage and the frequency is 60 Hz, and each phase voltage will be then shifted by 120 degrees. The load will be a 50 ohm pure resistive, and the delay angle in this case for the first situation will be 80 degrees. So that will be then the firing angle for these T1 up to T6. We will discuss how we do that in detail also, and how we also generate that in the MATLAB Simulink pulse generators. In addition, we will also calculate these parameters here, like the average load voltage up to the power factor here. So first, let's discuss what the conduction modes are for a three-phase rectifier using thyristors as the controller element. Now, if you have your delay angle alpha, which is less than or equal to pi/3 radians, which is 60 degrees, that means you have always a continuous current mode CCM for all passive loads. Or if you have a resistive load or capacitive load or inductive load, you will have for this condition a continuous current mode. If the delay angle alpha is larger than the 60 degrees, so pi/3 radians, then you will always have a DCM, so discontinuous current mode for pure resistive loads, but it might be also DCM for resistive inductive load. That is not really sure, so this is also depending on other parameters. And if your delay angle is larger than half pi, which is then 90 degrees, that means you have a DCM for all passive loads. So that means, again, the same situation actually as in the first part. So for resistive, inductive, etc., for pure passive loads, but it can be other things, so that is not valid for active loads like the batteries or back EMF or other battery-powered devices. The voltage expression for this circuit is shown here. We have the phase voltages also shown here actually, and we have also line-to-line voltage. And line-to-line voltage are actually the voltages between these two nodes, and also these two nodes. So those are actually the line-to-line voltages. These are called the phase voltages. The phase voltage expressions are shown here. We now change the t into the omega t, so we change our variable. That is convenient for the calculations we see shortly. The Vm here is the amplitude, so the phase voltage amplitude. And here the minus 2 pi/3 and plus 2 pi/3, those are the changes from degrees into radians. And the line-to-line voltages are actually shown here. You see here the VAB, which is actually between these two nodes, which is literally actually the VA minus VB. So if you do that calculation, you get actually this expression. Similarly for VBC, again from this node to that node, and the final one, which is from C to A. And you see actually here the changes also similar to what we see here in the phase voltages, but now you get also the square root of 3 and the phases will be different. How about the load voltage? Now the load voltage for the situation here will be given by the line-to-line voltage given by this VLL, and that is the square root of 3 times the peak value of our phase voltage, in this case 400 volts, so that will be in this case 693 volts. Okay. Now taking this together and now continue with the analysis and discussion using the graphs here. We see here the three phases. And by the way, this is now discussing the DCM. Why? Because we have the alpha of 80 degrees and that is larger than 60 degrees we have. And we have a pure resistive load, so that means we have DCM or discontinuous current mode. Okay. These are the phase voltages, so the three, which one? This is the orange, which is the VA voltage, the blue one is the VB, and the light green one is the VC. This is the load voltage, VO, and this is the load current, IO. so the pink one. You see also here where they start actually, this is the alpha minus pi over 6, so the alpha is our firing angle, and it is now coming back here at 0, at pi over 2, so half pi, and then getting up again at pi plus, alpha plus pi over 6. You see here clearly the DCM operation, because it is 0 and then coming up and then getting to again the 0 and actually stay at that 0 value for some time and then getting back again. This is definitely a DCM operation, which is similar to what we have seen also by the DC-DC converters. Now what happens actually here in more detail? Let's see that. The T6 here, which is the thyristor 6 here, that gate of that thyristor will be activated, and then the output voltage will come up, and also the current, of course. That will also happen for the T1, which is then happening at that moment. So the time that the output voltage and also the output current comes up is not at alpha, but alpha minus pi over 6 for DCM operation. And for T1, it is actually the similar situation, and for T2, T3, T4, and T5, etc. And then again, the repeated process goes back to T6, etc. And this distance here, you can see that clearly, which is pi over 3, and this also pi over 3, and also for that one. Okay, and those are the line to line voltages. So the part of the line to line voltage, it looks like a, let's say, a triangle, but this is actually a part of the sine wave we actually have across the load. That's also for this one, VAB. So we can use that part of the signal or the waveform to calculate for these values. And now we have the VAC here, VBC and VBA, and then it comes back again, etc. VCA first, and then this one. Okay. Let's now look at our calculations. We again have our DCM, that's already set. So the load voltage will be then used between this and that moment. So that's actually shown here. And that is then valid for alpha plus pi over 6. So the alpha in this case 80 degrees. And pi over 6 times 5, so 5 pi over 6. That's the region. And we have also the line to line voltage, which is square root of 3 times the VM, in this case 693 volts. So let's calculate the average load voltage. First question, that is the definition already shown here. So we have the 1 over the period, which is in this case pi over 3, and you integrate from alpha plus pi over 6 up to, you should say maybe alpha plus half pi, but actually you already stopped there, so you need to actually integrate up to this point, but you still divide by the complete period. Right? That's actually what's also shown here. And this is the expression for the VO. We actually take from here, and that's now shown here. Of course, 1 over pi over 3 is also effectively 3 over pi. That's also here given. And now we can move on and calculate that. So we can say, let's evaluate this integral. That's actually shown here. So we go from, we already also placed this VLL outside the integral because that's not dependent on the omega L. And when you now do the integral of this sine omega t plus pi over 6, which is then minus cosine of the same argument, and then you have the lower and the upper limit, you need to substitute here. That's actually also shown here. So in detail, you see here, first we substitute here for the omega t, this, so 5 pi over 6. And then the next one will be then alpha plus pi over 6. Now, let's make this simplified. We see here pi over 6 plus pi over 6, which is then 2 times pi over 6, which is then pi over 3. So minus minus will be plus. And this one will be cosine of pi, and cosine of a pi will be minus 1, so minus 1. With a minus in front of it, we will be then plus 1. That's actually what you see here. So this is the expression for the load voltage, average load voltage, for the situation DCM. So we can use this alpha to calculate now the average load voltage, and that's now done here. So we know the VLL, that's already calculated here. So we know also this alpha in radians, so you need to convert that 80 degrees into this radians, and you get here almost 155 volts. So we actually reduced our voltage tremendously, looking at the value 400 here. So we actually go almost to 155 volts. The next one is the average load current. That can be done in this case using Ohm's law, which is straightforward because we can use the average load voltage and divide by the resistor, and that will then result in 3.096 amps. Okay. The next one is about the RMS load voltage. That's question C. Again, we use a definition of the RMS value, which is the square root of the period, so 1 over the period, and then integrate the squared quantity, and we integrate also again between the two limits, lower and upper limits. Now we know already that it should be 1 over pi over 3, so that means then 3 over pi again in front, so I already made that change. And again, the same limits, and you see here now we need to square this expression, and that is actually shown here. So in order to square that, we can also square the VLL and also square this sine expression. That's already shown here. So we can also bring this VLL squared outside the integral. That has nothing to do with this omega t. So that's actually also done here. And also we can take it out even outside the square root, because the square root of the the VLL squared is just VLL, which is a line-to-line voltage. Okay, now we need to use now here the identity of the sine squared, which is actually shown here. So the sine squared x in general is a half minus a half cosine 2x. So we can use this. It will be helpful to evaluate this integral. So we will substitute here actually for x here, and I will use that expression and place it here so I don't have any squares anymore, so I can evaluate this integral much easier. So I have done that. So you see that here, this half will be just a half omega t or omega t over 2. So we will already integrating here. It will be minus 1 over 4. Why? Because you need to use the chain rule to compensate for this coefficient 2. That's shown here. And we get, of course, back to sine. And again, the same argument to omega t plus pi over 3. And then you need to evaluate that again from this lower limit up to upper limit. So how to do that? Again, you substitute here in this expression. First is 5 pi over 6, and you do minus when you substitute this value. That's actually shown here. The first one is shown here, minus the second one is shown here. So you see here the 5 pi over 12, which is this times the half, because that one. And you get also minus 1 over 4 sine, and there you need to do that 2 times, so 2 times this one will be then 2 times 5 pi over 6 will be then actually 10 pi over 6, which is effectively 5 pi over 3. So I did already some simplifications, and plus pi over 3, and then you do the similar form for the other one. Now we do alpha plus pi over 6 times the half, so everything gets actually divided by 2, and similarly for the argument of sine. Okay, now if we need to evaluate that, we look at again the values here. This is again the sine of what we see here is the sine of 2 pi. So that's gone. So the 0. We only have this 5 pi over 12 here. Of course, still this 3 over pi in front. That will hold for all the things. We have here the sine of 2 alpha plus, so we can also take this together as 4 pi over 6, which is also 2 pi over 3, and that will result in this one. So we see also here, and we also have evaluate these two, because that one minus the pi over 12 will be then effectively pi over 3. Now we can work out this 3 over pi inside this square brackets, so we can have 3 over pi times pi over 3, which is just 1, and also the other 2 parts, and then you get here the expression we actually wanted for our RMS load voltage, which is actually more work. You see actually that compared to the average load voltage, because we have this square and other things which will take some more time. So we have now our expression again, depending on the alpha we have chosen here. And this alpha is again in radians. So if you substitute that here, again also your VLL, here 3 times the radians, the delay angle, and you get here the 217.14 volts. Okay, for the RMS load current, that job is actually done quite easily, almost in 5 seconds. Just look at the, or use your Ohm's law actually, and then divide by 50 in this case, and you get here 4.343 amps. Similarly to the average load current, actually what we have done. Okay. Next one is about the absorbed load power. So let's go for that. And for that we can use this formula. Say actually the absorbed load power is the RMS load current That's one. Question D, squared times the resistor. In this case, we have already that from question D times the 50, and that will result in 943 watts. The next one is the power factor, which is the final question, question F. That is defined as the load power, absorbed load power here, divided by the apparent power S. So we need this apparent power, which is in this case 3 times the source voltage RMS times the source current RMS. So what are those? Now source voltage RMS is the phase voltage in this case, and divided by the square root of 2. So it is actually 400 over the square root of 2, which is then 282.8 volts approximately. And the RMS source current is actually the RMS phase current. These are the phase currents, by the way, IC, IB, and IA and IB. So we know the average value of the load current here and also the RMS value, so we can reflect that actually to the source current. And that's done using this formula. So we have here the RMS source current is equal to square root of 2/3 times the RMS load current. So you see RMS source current and RMS load current are related by this factor, which is then calculated here at 3.546 amps. So we know that. We also know the source voltage RMS, so we can substitute that in this expression. 3 times that one will be then 3009 volt amperes. And if you substitute here and use the value from question E, you get here 0.3134, which is a small power factor actually in this case. Okay, let's go and we collect here the values we just determined from A up to D, and we will now verify these 4. So those are now given here in the Simulink circuit. You see here the 3 phases, the thyristors, 6 of them, and also the gating signals from T1 up to T6. We'll also discuss this in detail shortly, how we can generate these signals. And we have here our load, and we have here also the scope here, and also some values we measure by mean and RMS components here. So let's go one by one. The first one is the average load voltage, which is here 155 approximately, 154.8, exactly as we have it. The average load current here 3.096, as we have it also. The RMS load voltage here is 217.1, so also what we have. And the final one is 4.343 amps for the RMS load current as we have it. So everything is correct, so this is nice. Okay, let's now see in more detail how we generate these pulses for the gates of this thyristor. So we look now at the pulse generator settings for our delay angles. So this is now the picture in the Simulink. You see here the T1 up to T6. Those are the 6 generators. There will be also 6 different settings in the delay angle. So we will see that shortly. And this is now also the scope, so just to see the plots here. And for this one, T1, I have actually now the setting here. You see here the calculation to do that. For the phase delay for the T1, you need to actually do that following. You do your delay angle plus 30 divided by the 360 times the frequency of operation, in this case 60 Hz. That's the formula. So we need to then take the 80 degrees here in this case, and that will result in 5.0926 milliseconds approximately. Why do we need to convert that degrees or maybe radians into the milliseconds? Because you need to also have it here in the Simulink that requires the phase delay in seconds. In addition, you need to put your pulse width here as 1/3, so that means 33.3%. And our period is also 1/60, so that's actually the frequency, 60 Hz. And I picked here just some value just to activate the thyristors here, just 5 volts, so it's really an arbitrary value. And we have now our settings done for the generator T1, which will then go for the thyristor here T1. The next one, T2, is similar. So what we do there is, now these are the settings you see here. And the settings are actually really similar to this T1. You see also again the 5 volts for the amplitude, 1/60 for the period, and also again this pulse width, which is 33.33%. What does it change? Really the calculation for the delay. So that's actually shown here. Alpha, again, plus 30, but now you need to add 6 degrees and you divide exactly by 360, again, exact same. So that will result in a different time. So it will be then 7.8704 milliseconds. And that will be then here. You see that actually that exact value. Okay, let's now discuss the other two, T3 and T4. So that's actually here, the settings. So we go actually in the similar form. So you look again 60 degrees later. So that's actually now in this case 10.648 milliseconds, and that's actually shown here. Again, the other settings are exact same as the previous two generators. And that for T4 is really similar also. And now you need to again add another 60 degrees, and that will be then 13.4 to 6 milliseconds, and that's actually shown here. So you see the exact same value here, and also for the T3. Now the final two, which is the T5 and the T6. Now you see here again the similar calculation. So I will add another 60 degrees. What I also have done is, this is not really necessary, but that is more convenient to see the signal clean at the beginning. I also did minus 360 degrees just to start it early, so I don't have this transient at the beginning. That is really not necessary, but it can be convenient. And if you do that, you will get this value, and that will be also here. You see that actually here, minus 0.000469296, which is this much microseconds. And for the T6, which is the pulse generator, and that is the setting here, and then again the similar calculation, again adding another extra 60 in the numerator, and that will result in this much milliseconds. You see actually that also here. Okay, now those are the settings you can do in the Simulink. Just to click on this pulse generator and then set the settings in order to get that alpha right for this three-phase controlled rectifier. Okay, now let's also look at the Simulink plots in our simulation. You see here again the phase voltage is up, so these are the VA, VB and the VC, and this is again the load voltage and the load current. You see also some labels, so I will go through them also. So the first label here is where we actually see our 120 pi times this second, which is 0.002314 seconds, so it's actually this much milliseconds, and that will result in 0.8724 radians. What does it mean? Now we know from a discussion of the graphs for the DCM condition that the alpha minus pi over 6 was actually our beginning, so it was actually where this signal we are starting. This is actually what you also see here. So this actually, if you do the calculation here, we get exact or exactly very close to what we see here. So this again alpha from delay angle from our assignment minus the pi over 6, and that is then actually shown here. So it is very close. The rounding off errors are actually just a simple difference here. The next one is about this red curve here. I mean the label here. You see here the 0.004167 seconds. So again, I convert that to radians. You do that by using the radian frequency. So you do 60 times 2 pi times this time, and then you get the radians. And that was at pi over 2. And that's actually also shown here. So pi over 2. These two values are again matching nicely. Another one is happening at this label, which is what we have calculated as, in this case, 120 pi times 0.005092, that's shown here, and that is the 1.9196 radians, and that should happen at alpha plus pi over 6 radians, and that's, if you do the calculation here, you see actually they also are actually also matching very well. So we see indeed that this is indeed correct. Okay, let's now go to the continuous mode or continuous current mode for this situation, and we change now only one thing here in this circuit. That's the delay angle. We make it 50 degrees. It was 80 degrees, now we make it 50 degrees, which is also equivalent to 0.8727 radians. So with the CCM in this case, because we know that is lower than 60 degrees, which was the condition we have discussed at the beginning. Now this is the general plot again. You see here the situation for the CCM. Well, now why is it CCM? You also see that this curve, which is the load current, is not coming to the zero value, it is staying above the zero value. These are the phase voltages again, VA, VB, and VC. And this is now the load voltage again, and the load current. And those times are when the T6, T1, T2, T3, T4, T5, and T6 will be activated. You see actually here. So delay angles will make sure that these thyristors will be activated. That creates actually this jump up and then getting back and jump up and getting back. So each time the thyristor will be activated, you see actually here the changes, rapid changes in the currents and voltages. And these are again the line-to-line voltages. You see that in this case, clearly it is not a triangle, actually it is sort of a shape of this voltage part. So also for this VAB, where we use the actual value later for this part, and VAC, etc. for the other parts. And then it will repeat actually from the VCB. You see that actually here, so because this one is VCB, and again DCX is the same thing here also. So you see now here that this will be starting at when the T1 is triggered. That will happen at alpha plus pi over 6. And the other one will be then later, which is then alpha plus pi over 2. So this is now the distance here, and now the period is also here pi over 3, same as the DCM condition. That doesn't change, so the period will be the same. The only change here will be where you start and where you actually end. And also, of course, your waveform is not anymore reaching 0. Okay. Let's now again present here the load voltage, which is in this case VAB, which is a line-to-line voltage from between node A and node B here. It's again this expression we already know, and that is then given here the line-to-line voltage for 693 volts. We know it is now again different because it is now alpha plus pi over 6 up to alpha plus pi over 2. So we need to calculate using these two regions. Okay, we again use the formula for the average load voltage. This is actually the formula again, so 1 over the pi over 3 actually, and then it will be result in 3 over pi, and then integrate this. That's actually shown here, so we substitute actually this expression here, and now you can calculate that, again evaluate in a similar form. So we evaluate this sine, we make it minus cosine the argument, and the VLL will be taking out of this integral, and that will result here as you substitute first this one and the next one that one, and you have now the result, which is easier actually and more simple than the DCM condition, which is 3 times the line-to-line voltage over pi times the cosine of alpha. Now we know our alpha, so we can substitute here the value, and that will result in 425.3 volts. Okay, now we know that A, we can now calculate actually B using again Ohm's law, which is straightforward. So you divide by the resistor, 50 ohms in this case, that will result in 8.505 amps. Okay, now getting to the next job, which is our RMS load current, RMS load voltage, which is more work. So that is the next one. So I will now make again the definition. So use the square root of again the period, so 1 over the period I must say, and then integrate from the lower up to the higher limit, upper limit. So that's actually again the signal will be again squared. So we see again here the situation. Taking this situation again here, so VLL squared can be again taking out the integral, but also taking out of the square root because it is a square of a square root. So that's just VLL, and you only have this one. Again, this identity can be used to make this more simplified, and that is actually shown here. We also have discussed this in detail for the DCM mode. Okay, now we have this, so we need to integrate that. So we will do that. That's the next step. So what I have done is the half is just again half omega t, and the other one is just minus a half times 1 over 2 again because of this chain rule. We also have discussed in the DCM, and now we have this lower and upper limit also for our integral. Okay, now we first start with the alpha plus pi over 2. We substitute that first. Of course, we need to divide by the 2 here, so we need to also do alpha over 2, and then plus this over 2, which is then pi over 4. And similarly for the argument and the sign, and also for the other part. So that's actually what we do here. Now what do you see? We can already see that the alpha over 2 and a minus alpha over 2, so that will cancel each other out. That's nice. Now pi over 4 minus pi over 12 will be then pi over 6. That's effectively that. And you also see here the sign of an argument, which is different there, but they have both 1 over 4 in front. So I have also here minus, and minus will be plus. So what I do is I will do plus 1 over 4 times first this one in the parenthesis, of course, and then the minus that one. Now we will use the identity, or you can use phasor calculations to convert these two sine expressions into one sine or cosine expression, and it's actually done what I have here. So you see here the expression, and that will result in the square root of 3 times the cosine of 2 alpha, which is exactly equal to this expression here in the parentheses. And times of course 1 over 4, and that will result in this. And now again you see here 3 over pi times pi over 6, which will be then half, and it will also go inside, and you get actually this expression for your RMS load voltage. Again, we need to calculate here that using the delay angle alpha. So we will do that. We know the VLL, which is our line-to-line voltage, and that will result here in 453.4 volts. Now, the question D is actually pretty simple because we know the RMS load voltage, so we can calculate RMS load current by using Ohm's law again, and that will result here in 9.067 amps. Okay, taking all this together, and also this one, we go to question E, which is our observed load power. And that's again the square root of the RMS load current times the resistors. That's shown here, and that's in this case 4,111 watts, so almost 4.1 kilowatts. And the power factor, for that we again use a definition, the observed load power over the apparent power. Apparent power is again given by this expression for the three-phase system, so 3 times the RMS source voltage times the RMS source current. RMS source voltage is this Vm, which is our phase voltage amplitude to 400 over the square root of 2, that's this value. And the RMS source current is the RMS phase current, as we have discussed, because that this current, this current, this current, but that is related to the RMS load current actually by this expression. Also what we have seen in DCM, and that will result in almost in 7.4 amps. Now we know everything, so we can calculate here the S, so 3 times this, times that, and that will result in 6,282 volt amperes. We can now substitute that in this expression, and that will result in 0.65 approximately as our power factor. Okay. Let's now go to the Simulink circuit and see the results for these 4 calculations. See here again the thyristors and the 3 phases in the 3 phase voltages in star connected configuration. Let's go one by one. The average load voltage here, which is then displayed here, this is 425.3, which is also what we have. The average load current is 8.505 amps, also what we have. The RMS load voltage is 453.4, also what we see here, and the final one is RMS load current, which is then 9.067. So also what we have here, so that's all perfect. Okay, let's see also the settings for the pulse generators for the delay angles. Also for this example, it was really similar. The only change is really you make this 80 degrees, which you had before, you make 50 degrees. So I go a little bit faster because I already did that in more details. That's actually the calculation. See again here the alpha and plot 30, that's actually where you start, and you divide by the 360 F, which is the frequency, and now you calculate that in milliseconds. That's actually what you see here. And for T2 in a similar form, so I go a little bit faster, you now add to plus 60, and then you get now this almost 6.48 milliseconds, also what you see here. Okay, now go to the T3 and T4. So let's bring all the data here. You see again the calculations for T3 and T4. You will add another 60 each time, another 60 for each thyristor gating actually, and then you see here 9.26 milliseconds and here 12.04 milliseconds approximately, and you also see that here and there. Okay. The final two are the T5 and T6. So the T5, you can do that again using the same, but now again adding up another 60, and I also discussed that for the DCM operation. I do minus 360 just to start at the same time, so we don't have any transient effects. So this actually is minus 360 degrees there, and that will result in this minus 1.8519 milliseconds. For T6, I have the similar situation, but I will add another 60 and again minus 360 just to compensate, and you have here now 925.9 microseconds. That's actually shown here. The other settings like the amplitude, the period, and the pulse width are exact same as before, so just 1 over 3 here. So as the percentage is then 33.33, 1 over 60 because 60 hertz, and just 5 volts just to activate the thyristors. You can also make maybe 4 or 6, it doesn't matter really, but just to activate the thyristors. Okay, in this case we look also at the Simulink plots. So we see here again the phase voltages VA and VB and VC. So the brown, the blue, and the light green one. Load voltage and the load current. We see also labels, so let's go one by one and so verify that the calculations are correct. So first label here in blue, that is happening at 0.003703. And if you now convert that time, this is a time in seconds, in the radians, you need to multiply that by the radian frequency, which is 2 pi times the 60 hertz. That will be then 1.4 radians approximately. And we said that our signal was starting at alpha plus pi over 6, which is in actually this calculation, which is really similar, so it's also correct. The next one is this one. You already see actually this signal, which is our load current, will not reach 0, and that is also what we say the CCM. So we don't see actually there's a region where it actually stops and then some part 0 and then comes back again at some other point. Here we have another label, which is 0.006481 seconds. If I now calculate that also, and then there will be then 2.44 radians approximately, and we know that will happen at alpha plus pi over 2, and if you now do the calculation here, you get here 2.4435, which is very close to what we see here in this Simulink plot also. So it's all nice and correct. Okay, let's now make a summary and also compare the results for the delay angles we have discussed, which is the 80 and the 50 degrees. So we see here the conduction mode, DCM and the CCM. Again, the alpha is 80 degrees and alpha is 50 degrees. This is only valid, by the way, for resistive load, because we don't discuss any resistive or inductive load here. So these are the parameters we have calculated. So the load voltage, average load voltage, average load current, up to the power factor. So what do you see actually? You see actually a couple of things. So the conclusions, you see the voltage here for the DCM is lower, and also the currents are lower, much lower actually. You also see the absorbed power is much lower, and the apparent power is also much lower. And also, by the way, that power factor, which is a very important parameter, is much smaller, almost more than actually 2 times smaller than the CCM. Our conditions then increasing the delay angle will result in reduced voltage and current at the load, and a power factor reduction, which is of course not a thing we don't want. So this is of course a thing we need to consider. So this is I think a nice comparison between the DCM and the CCM for this 3-phase rectified circuit we're having a resistive load. Alright, this was our example considering the 3-phase rectifier using the thyristors as the controlling element. We have looked at how we can calculate the components and the parameters here for this situation, and also discuss in detail how you do that in Simulink to activate the gates here from T1 up to T6. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.